like this. I will I will go more quickly on the first the first part of my talk to come to the more the newer part of it. So what I first, I would like to say there are several bits joint work with Stefan Haller from Vienna, with François Gay-Balmaz from Paris, my longtime collaborators. This is work in progress with Jerry Goldin, and also with my PhD student, Joanna. And I will, so I'm really coming from geometry in infinite dimensions. So please excuse if my point of view to fluid dynamics is very primitive in some sense. I'm studying this singular vortex configurations really from the point of view of geometry. So I'm interested in those coadjoint orbits, not in the dynamics in this talk. So I will start with quickly recalling that the ideal fluid flow can be seen as a geodesic equation on the group of volume preserving diffeomorphisms of a Riemannian manifold. In my talk, the Riemannian manifold will be R2 with the Euclidean metric. And I want to recall the work of David, which I think it's cited in more than half of my papers. I put here also the first page of this paper with Jerry, and I will not insist on this. So as I said, the group I'm in two dimensions. So the group of volume preserving diffeomorphism is actually a symplectic group, and so I'm and R2 is contractible, so it's really the Hamiltonian group. And it's important that the Lie algebra, which are the compactly supported Hamiltonian vector fields on R2, can be identified with the compactly supported functions on R2. With the we can uniquely find the Hamiltonian function with the compact support. So the dual space is really the space of distributions. The vorticity lives in the dual of the Lie algebra. Here I wrote it in general that so the vorticity 2 form is the differential of U flat. Flat is taken with respect to the Riemannian metric. And so we have the equation for the in vorticity form. And if in general, the dual to the Lie algebra of divergence free vector fields is the space of one form modulo exact one forms. We've seen it also in Tudor's talk a lot. But if H1 of n is 0, then it is identified with exact two forms. So here is the distributions. But in our 2D setting, we just, in the regular case, the vorticity is a function. And then I took this picture from one of the paper of Anton and Boris, where they classify this in the smooth dual, some coadjoint orbits, and they use these Rebe graphs. But I'm interested in singular vorticities, so in distributions that in coadjoint orbits that live in the space of distributions. But I will take distributions that have controlled singularities, that they are supported on nice submanifolds. Now in R2, we don't have so many. So that's why, so these are the 6 cases that I I want to talk on. I think I have the picture here. I will talk first on point vortices, and then on dipoles, on vortex dipoles. So these will be finite dimensional coadjoint orbits. But then I take the vortex loop, so one can see it as a continuous family, a curve of point vortices. So it will be a weighted curve, so a curve with a weight attached to it, the vorticity distribution. And then I will go on to the pointed vortex loop. So I take a vortex loop and extra points on it. And then I will attach dipoles to a loop, to a vortex loop. And in the end, I will take a continuous family of vortex dipoles. In cases 1, 2, 4, and 5, the KKS form, the Kostan-Kirillov-Suryo symplectic form on the coadjoint orbit, is exact. But in the cases 3 and 6, it is not. So that's why we get, and there we get these pre-quantization conditions. In the first case, so for vortex loop is the enclosed area A times the total vorticity W must be integral, and for loop of dipoles, it is the area of the parallelogram formed by the dipole vector and a tangent vector that is dual to the vorticity 1/4, to the distribution on the loop. I hope to come to this number 6 because this is the newest. It's very new. You will see it also from the slides. There are just handwritten slides on it. So the tool that we are using in detecting the coadjoint orbits is the momentum map. And here I recall the definition of the momentum map. It is the contraction of the symplectic form with an infinitesimal generator of the Lie algebra element X is the differential of the of J paired with X. So this is a Hamiltonian function for the infinitesimal generator. And the momentum map for the coadjoint action of G on O is just an inclusion. And the other way around, so yeah, I wrote it in a lemma. If we have a group that acts by a Hamiltonian action, and the momentum map is injective and equivariant, and the third condition, the action has to be transitive. Then M is a coadjoint, or the image of M is a coadjoint orbit, and the KKS form and the form omega, they're correspond each other through the momentum map J. So this will be our the method. Here is the plan of my talk with the 6 types of singular vorticities. And now I will go to the first one, point vortices. We have, sorry, first I had big N, and then I decided to have K, and there is an N left here. So I take K points in the plane, distinct points, so they are in the configuration space of ordered points in R2, denoted by conf K of R2. So we take out the fat diagonal, and we endow it with the symplectic form that comes from each factor, but multiplied with the circulation, with the strength of the point vortex gamma I for xi. As I said, the inclusion will be the momentum map, as we've seen in the lemma before. So this J will come over and over again in different settings. So here to a K tuple, we assign the distribution, the delta distribution gamma I delta xi, and in this way, we identify a coadjoint orbit. The configuration space is a coadjoint orbit, but only when all the vorticities are distinct, because if we have 2 vorticities, let's say gamma 1, gamma 2, then interchanging 1 and 2, x1 and x2 gives us the same distribution. So J is not injective if some of the vorticities are equal. Let's denote by sigma gamma the permutation subgroup that preserves the partition of equal vorticities. And this is the group we will have to divide by in order to get an injective momentum map. And the KKS form will come from this omega gamma, which is which we had before. So in the most symmetric case, when all the vorticities are equal, we will get the coadjoint orbit will be the configuration space, this time of unordered points in the plane. And if all are distinct, then we have the ordered configuration space. So this was point vortices. Now let's move to vortex dipoles. I don't have a picture here, so it is dipoles that like the electric dipole. So one dipole can be obtained in two ways, either by taking 2 point vortices with equal and opposite strengths and approaching them such that the product between the distance and the circulation is constant. And so in the limit, when the distance goes to 0, it's the vortex dipole. But also we can also take a source and a sink and to do also to identify them, and one obtains a dipole. But what remains is just a vector in the plane. So V is I don't know, by xv, V is a tangent vector at the point x in the plane. And now we are preparing for the KKS symplectic form. We identify the cotangent bundle with the tangent bundle using omega, the area form. And and we transport the canonical cotangent bundle symplectic form and theta, the one form, the potential of it. And what we get are these formulas. So here a tangent vector at V to the tangent bundle TR2 has two components, U and A. U is the horizontal one, A is the vertical one. And so these are the formulas for the one form and the two form. And indeed, the Hamiltonian group acts on the plane, acts on the tangent bundle in a Hamiltonian way, and the momentum map is the one that we expect for a dipole vector, the vortex dipole. It's just the derivative of the function in direction V. And in this way, we identify, but we have this cross means that we take out the zero section. We don't allow zero vectors. One can consider also several vortex dipoles, and we get, because there are no analog of the gamma i's we had before. So there is really a symmetry, and we get the unordered k-tuple of dipole vectors. So now we go to the vortex loops. So we have this point vortices that are on the curve, and this is a special case of vortex sheet. Also, Boris has studied vortex sheets in 3D. So there we have surfaces. Also with Francois Gay-Balmas, we have a preprint on it. So let C be the curve, and the beta is the vorticity distribution. So it's nowhere zero. Actually, it's a one form. One can consider also densities. Then we can take also unoriented curves, so the momentum will be, so distribution is just integrating the function h over the curve with the one form beta. The action is of the Hamiltonian group. I will denote by big G the Hamiltonian group, and it's just by push forward. And I will use this identification of non-parametrized curves with one form. We can identify them with parametrized curves modulo rotations of S1, and here is the identification. So because the W is here W is the total vorticity, so the integral of beta over the curve. So that's why beta is the push forward of the canonical one form dt on the circle multiplied by that W. And the other way around, if we are given C and beta, then we just integrate beta to obtain the parameter T of the point X. And but here we made a choice, X0 to have parameter 0, and taking other choices, we get reparametrizations by rotations. So what are the invariants of the action? Since it's area preserving, the enclosed volume is preserved, and I will denote by new potential of omega. So omega is the one form on R2, so the new is omega, and also the total vorticity is preserved. The coadjoint orbit for the vortex loops will be such pairs C beta with enclosed area A and total vorticity W, or identified with in the parametrized form is MA. I denote by MA the embeddings that have such that the image has enclosed area A. Each such coadjoint orbit contains one circle with uniform distributed vorticity. So we can deform any curve to a circle and also to make beta to be equally distributed. So this maybe these are special cases of the coadjoint orbits, the weighted Lagrangian submanifolds considered by Weinstein, by Alan Weinstein, and then by Lee, yes, these are just low-dimensional versions of them. But one can get them via a dual pair. And this dual pair appeared already in the paper, in the talk of Tudor. So here, I just recall it briefly, here S is endowed with the volume form, and omega, M with the symplectic form omega, and we cook out with them a symplectic form on the space of embeddings. And then we have the actions. From the right, it's the group of volume preserving diffeomorphism of S, and from the left, the Hamiltonian group of M, and then we get when omega is exact, we get this dual pair. I chose this simplified version because our area form is exact. There is a general, so these two groups, the action of these groups is, they are mutually completely orthogonal actions. This means that the orbits are symplectically orthogonal to each other. So as a consequence, the momentum maps are also have the kernels symplectically orthogonal to each other, which is the definition of a symplectic dual pair. And these are the momentum maps. On the left, we just push forward by the embedding the volume form, and we get a singular distribution on M. And on the right hand, it's just the class of the pullback of the one form. And this is in the regular part of the dual. And we really used it with Francois to get some of the coadjoint orbits obtained by Weinstein, and because we were doing only, yes, so by doing symplectic reduction at 0. So I don't know. So there is this general principle that if we do symplectic reduction on for one group, we get coadjoint orbits for the other group. So we do symplectic reduction on the right leg, and we will get coadjoint orbits on the left one. And now in our case, when S is S1, and the volume form mu is just WDT, and R2 and M is R2 with the area form, then the right leg is just given by the area. It's the area, the enclosed area. So when we do reduction at some and then let me show again here. Then here on the right leg, we will have the Lie algebra of the rotation group, which is just one-dimensional. It's R, and GR is just giving the enclosed area, and then we do reduction, and by reduction we get exactly the coadjoint orbit the vortex loops that we had before. So the KKS symplectic form is just the reduced symplectic form. It descends from this omega. And it is realized as a symplectic and as a coadjoint orbit by the left momentum map. And here we recognize the integral of H over the curve with beta. So I think I will skip this. I will even so let me come back. Even so the symplectic form omega is exact, because big omega is exact because small omega is exact. The reduced symplectic form is not exact. And so we can ask when is the symplectic, the coadjoint orbit, when is it prequantizable? So what is a prequantum bundle over the coadjoint orbit? Is a principal circle bundle over O, I denote by O sigma, the coadjoint orbit, and it is endowed with a principal connection, so it's a one form, such that the curvature is the KKS symplectic form. And there is this theorem that a character exists for the element in the Lie algebra if and only if the coadjoint orbit is prequantizable, and the coadjoint action can be lifted to an action on the principal bundle by connection preserving automorphism. What is a character? Is just integrating the element in the dual to a homomorphism on the isotropy group G sigma with values in S1. So when is our coadjoint orbit prequantizable? We have a candidate for a prequantum bundle. It's the space of embeddings, this MA S1 R2, the embeddings that have constant enclosed area. And we have also a candidate for the one form, because the pullback of the KKS symplectic form to embeddings is the differential of this one form, which is constructed with the nu. Recall that d nu is omega, small omega. But in order to be a principal connection, it has to reproduce the infinitesimal generators. And the infinitesimal generators for our action is the velocity along the curve, so the f prime, the derivative of the parametrization, and we get W times the enclosed area. So AW should be either 1, or it can be also something, an integer, because if it's an integer, we can factorize by so it's if the product is equal to K, then we can factorize by the subgroup ZK, the cyclic subgroup generated by the rotation by angle 2 pi over K, and then by this rescaling we will get that the nu theta will reproduce the infinitesimal generator. So we have this result that joint with François-Gay-Balmas, that the orbit is prequantizable if and only if AW is in Z. Or a similar result has in the case of R3 and for vortex sheets that are open surfaces in the paper of Goldie, Menikoff, and Sharp. One can see this also using the character. So here is the paper in 87 that I mentioned before. That one can give a geometric description of the character. So if the element, we take the element in the dual of the Lie algebra that is defined by the pair C beta, the curve and the vorticity distribution, then we take any curve that comes from infinity to the point X, and then phi is an element of the Hamiltonian group, and we take its image, and but phi is in the isotropy, so it preserves the curve. So phi of X has to be on the curve, and the area. Then we take we consider the area of the triangle that is formed, and we integrate it over the curve with the one form beta. And here one can see that if we go once around the curve, then what we get is, so then we add the area times the W, which is the total total vorticity. So really A times W has to be an integer. So these were the vortex loops. So now we will put some points on them. If we put the points, then so we have k points, x1 and xk. So they belong to the curve. So this is going to work with my PhD student, Ioana Ciuclea. So what we have is a curve and some points on the curve. And we look at vorticities of this type. So we integrate over the curve, but we also add these point vortices with circulations gamma 1 to gamma k. And now, because what are now the invariants of the coadjoint action? So again, of course, the enclosed volume and the total vorticity, but we have and the circulations. But we have new invariants, which are these vorticities that are between two successive points on the curve. And these add to the total vorticity W. And if we have such pointed vortex loop that satisfy these that have these invariants, then we can associate in a unique way an embedding. And now there is no ambiguity with reparametrization by rotations, because we will fix, for instance, x1 to have parameter 0. And then the parameters from the next points will be, so this T1 to T6 are just parameters that are prescribed by the these local vorticities W1 to WK. But similar to the case of point vortices, we have when there is some symmetry of the vortex data, then we don't get the momentum map, we don't have the momentum map J injective. So if you write the vorticity we had here in the language of embeddings, we get this distribution. So, and we see that if the data have, the vortex data, gamma I, Wi have some rotational symmetry, this means that there is an L smaller than K, or equal to K if there is no symmetry, such that gamma I plus L is gamma I and Wi plus L Wi, then we can do some rotations, namely rotations by 2 pi over K null, K0, where K0 is K divided by L. L will have to be a divisor of L of K. And but it gets more interesting when we work with densities, because then there is not just a cyclic group, then we have really the dihedral group, so that we can look for dihedral symmetry, and the regular K-gon will have the gammas on the vertices and the W's on the edges. So this is how the action of the dihedral group will be. So if we factorize by this, we will get an injective momentum map, and then we really have our coadjoint orbit of pointed vortex loops. What I find interesting here is that we have the same space but different KKS forms, so which depends on the number of points, and it depends on the local weights. And what is also interesting is that if we write we can find canonical coordinates for the symplectic form, namely here we decompose the vector fields along the curve into normal and tangent parts, normal and tangent to the curve with respect to the Riemannian Euclidean metric. And then since we have since the area inside the curve is preserved, the normal component, so it's given by zero integral functions on the curve, but the tangent one is can be arbitrary, but there is a duality between these two spaces, a non-degenerate pairing, which is yes, the one that we can also guess from the KKS form. This is because we are infinite dimensions, because we see that this is a subspace of the other one. Now we will put dipoles on the loop. Okay. So now we have this vortex loop, this weighted curve, a curve and one form on a density, and a vector in the plane that is based on x, and x is on the curve. And this is the distribution we'll look at. We integrate the function over C, and then, but we also take the different derivative in direction V. And we could also add some point vorticity at x, some gamma h of x, if we want. And what are now the invariants of the action of the Hamiltonian group? Again, the enclosed area, the total weight, but also the area of the parallelogram that is formed by the vector, and T is a vector field along the curve that is such that beta of T is W. So, and now we have the point. So when we identify the unparametrized weighted curve with the embeddings, again, we know where to start to get the parametrization. So it's a one-to-one correspondence. Again, the pullback of beta is W dt. And because of this, the vector field big T is just here is a misprint, is f prime, not at 0. Then here I should have put t at point x in this formula, because v is at point x. But so in the end, the candidate for the coadjoint orbit is given by pairs of parametrization f, the embedding f, and the one vector v, such that v is tangent at f of 0. So f of 0 is our x, and we have this a constant parallel area of this parallelogram, and the KKS symplectic form. I recalled here the one for vortex dipoles, so that we can see that the KKS form in this case is built out of the KKS form for vortex loops, but on the space of embedding. So before doing reduction, before factorizing by the rotation group. And here is the one for vortex dipoles. So what we get here is that the coadjoint orbit is a symplectic submanifold of the product of two coadjoint orbits that we discussed before, the vortex loops and the dipoles. And but it's interesting here because for the vortex loops, the KKS form is not exact. We had this pre-quantization condition, but still here, when we pull back the product of symplectic form to the coadjoint orbit of dipole vortex loops, it will be exact. So this is the KKS form here is exact because omega is exact. Now we take these dipole vectors along a loop, but this we will get in the end. First, because I will get to this coadjoint orbit via dual pairs. And it is a dual pair that is closely related to the EPDiff dual pair due to Daryl and Jerry. And Daryl talked about this today. So it is this dual pair on the cotangent bundle to the space of embeddings. And we have the left and right actions of the diffeomorphism groups. And the left one is the singular solution and the right one gives conserved quantities. My alpha F is the pair PQ in the talk of Daryl, because later F will be the embedding of the circle in R2. I just want to mention two other, another dual pair, because it is related to the contactomorphism group, and David and Steve have a paper on this group, and so it's the and the Euler-Poincaré equation on this group. So the Euler-Arnold equation on this group. It is here I wrote it in the special case when the contact manifold is the projectivization of the cotangent bundle, Xi is the canonical contact structure on this projectivization, and then there is a natural inclusion of vector fields on M into contact vector fields on the projectivization. And so here on the left leg, instead of having so the left momentum map is lifts to this, so so via this the pullback of this inclusion, so it's related to the momentum map, the singular solution for the EPDiff equation, and it is again a dual pair. So with Stefan Haller we proved this. It was this was a difficult paper. It appeared in Mathematische Zeitschrift. But now for the dual pair that I will use to get the coadjoint orbit that I'm talking now is by restricting the before in the EPDiff dual pair, the action from the left is done with the group of diffeomorphism of M, and now we restrict to the group of volume preserving diffeomorphism of M. So we take volume form on M, but moreover we need the exact volume preserving. This is the, I gave here the definition. It's, when we contract the vector field with the volume form, we get the differential of an n-2 form, which is the case with our Hamiltonian vector fields. And if the dimension of M minus dimension of S is greater or equal than 2, so the codimension will be for the submanifolds will be at least 2, then we get a dual pair. So the maps GL and GR are exactly the ones that we have that are in the Holm-Marsden EPDiff dual pair. Here we can perform symplectic, again the general principle, perform symplectic reduction on the right leg, and to get coadjoint orbit on the left. I'll just show you the special case when S is the circle and M is R3. We all know this Marsden-Weinstein symplectic form on the space of unparametrized knots, which is if we have tangent vectors, normal tangent vectors along the curve in R3, we contract them with the volume form and integrate over the curve. So this is and this is the KKS symplectic form on a coadjoint orbit. So I denote here by GR1 R3. So this is the nonlinear Grassmannian, the analog of the linear Grassmannian. So it's nonlinear one-dimensional object in R3, which are the curves. So you take the closed version. So this is known to be a coadjoint orbit, but by doing the symplectic reduction in the EPDiff vol dual pair that I just talked about, one gets that also the cotangent bundle to the space of unparametrized curves, the regular one, is with the canonical cotangent symplectic form, is coadjoint orbit of the group of volume preserving diffeomorphisms of R3. But what happens? I am interested in curves in the plane. So it is the codimension 1 case. So what happens? What can we say when the dimension, the difference between dimension of M and S is 1? So the codimension 1 case. Then we have to restrict to make two restrictions. First, we have to restrict to one leaf of an analog of Weinstein's isodrastic distribution. So the isodrastic distribution is defined with the symplectic form, and this one is defined with the volume form. In our case, we will have omega instead of mu, so it will be really the isodrastic distribution of Weinstein, and one leaf will be our MA-S1-R2, the embeddings that have an enclosed area constant equal to A. So the first one,
you
yes?
just have just a few more minutes left.
Okay, thank you. And then we have to restrict also to elements that when we apply the right momentum map, we obtain here nowhere zero one-form densities. And if we do this, then we get again a dual pair. So this is the EPDiff vol dual pair. And in the special case when S is S1 and M is R2, here we will have the dual of the space of functions. And when we do the reduction, then, and now I have to switch to my notes. If we do reduction, here it is. The reduced symplectic manifold will be, so we do reduction at one form density that is constant, because it's clear this is nowhere zero, and every row that is nowhere zero is with the diffeomorphism of S1 can be we can bring it into the constant one, and so we will have this yes. There are a few more things to explain here.
Yeah, perhaps this is a good place to stop.
To stop.
The next talk is at 12:30, and we would perhaps maybe some people may want to ask questions.
Okay. Then I will stop like this, and thank you for the attention, and tell happy birthday to David. Thank you.
Yes, thank you. Okay. Any questions?
I have one. You can hear me, right?
Yes, I have. I can.
So the in the first case you mentioned, you have point vortices, and you can restrict the Hamiltonian and just get a system of to describe the evolution of those point vortices. Can you get the same sort of system for the other 5 cases, like restrict the Hamiltonian to just the space of curves and then watch that go with the symplectic form that you've already derived?
Yes, so it's always delicate. We know already from the point vortices that it's not. So you say now to look at dynamics.
Exactly.
On this, yeah. So this is another story, and each of these cases would need I guess a different approach. We know already from point vortices that it is one has to do some. I never always forget how one says that. Or not don't immediately recognize the ideal fluid flow. So one has to do some simplifications. Or this localized inductional approximation for curves. So it's yes, I guess in each of these cases one should do something like this, but I'm not a specialist in this.
So are those all open as far as you know?
As far as I know, yes.
Oh.
We can't hear you. At least I can't.
Okay. Yeah, I was just asking if those questions are all open for the other 5 cases.
Yes, as far as we studied a bit the vortex sheets, but not in 2D, in 3D. So no, I don't know.
Okay, perhaps we can stop now and thank Cornelia for the talk.
Thank you.